Today, we are going to do more than answer a step 1 question. We are going to take the question apart piece by piece. We'll identify what the question is really testing, compress the vignette, find the pivot clue, dissect every answer choice, and then look at what your answer may reveal about the way you reason under pressure. Before I explain anything, keep track of 4 things. What was your first answer? What was your final answer? Did you change it? And how confident were you? Here is the question. A 22-year-old woman is brought to the emergency department 4 hours after ingesting an unknown number of tablets during an argument with her partner. She has nausea, vomiting, dizziness, and ringing in her ears. Her temperature is 38.1 degrees Celsius. Her pulse is 112 beats per minute. Her respirations are 30 per minute. Her blood pressure is 118/72. She is anxious but oriented to person, place, and time. Laboratory studies show a sodium level of 140 milliequivalents per liter, a chloride level of 104 milliequivalents per liter, a bicarbonate level of 16 milliequivalents per liter, and a glucose level of 96 milligrams per deciliter. Arterial blood gas analysis shows a pH of 7.46, a partial pressure of carbon dioxide of 24 millimeters of mercury, and a partial pressure of oxygen of 102 millimeters of mercury. Which of the following best describes this patient's acid-base disturbance? Choice A, acute respiratory alkalosis with appropriate metabolic compensation. B, anion-gap metabolic acidosis with appropriate respiratory compensation. C, mixed respiratory alkalosis and anion-gap metabolic acidosis. D, mixed respiratory acidosis and non-anion-gap metabolic acidosis. Or answer choice E, metabolic alkalosis with appropriate respiratory compensation. Pause the video or go back through the vignette and lab data now and give yourself about 90 seconds to answer. Welcome back! The correct answer is choice C, mixed respiratory alkalosis and anion-gap metabolic acidosis. But getting the correct answer is only the beginning. The more useful questions are, how do we prove it? And if you missed it, where exactly did your reasoning break? The combination of tinnitus, nausea, vomiting, fever, and tachypnea should make you think about salicylate toxicity. But this question is not asking which substance she ingested, it is asking you to classify the acid-base disturbance. So this is not primarily a toxicology diagnosis question. It is an acid-base interpretation question. That distinction matters because students often recognize the disease and then choose an answer based on a memorized association. Here, we want to prove the disturbance directly from the laboratory data. Acid-base questions are best solved through a consistent sequence. Start with the pH. Determine which variable is moving in the same direction as the pH. Calculate the anion gap when appropriate. Then test whether compensation is appropriate. Only after completing that sequence should you commit to the final answer. Now let's compress the vignette. If you remember, she ingested an unknown number of tablets, she has tinnitus and tachypnea, her pH is 7.46, her carbon dioxide level is 24, her bicarbonate level is 16. That is the core of the question. The values we need to carry forward are a pH of 7.46, a carbon dioxide level of 24, and a bicarbonate level of 16. Start with the pH. The pH is 7.46. That means the patient is alkalemic. So the dominant process pushing the blood pH is an alkalosis. Next, look at the carbon dioxide. Her carbon dioxide level is low at 24. When carbon dioxide falls, the pH rises. So the low carbon dioxide is moving in the same direction as the alkalemic pH. That confirms the presence of a respiratory alkalosis. This is where many students stop. They see an alkalemic pH, they see a low carbon dioxide, and they choose acute respiratory alkalosis. But identifying one true process does not prove that it is the only process occurring. We still need to account for the bicarbonate. Her bicarbonate level is 16. That is also low. But a low bicarbonate pushes the pH downward toward acidosis. So now we have two abnormalities moving in opposite directions. The low carbon dioxide is producing alkalosis. The low bicarbonate is producing acidosis. The next question is whether the bicarbonate is merely compensating for the respiratory alkalosis or whether it represents a separate primary metabolic acidosis. To answer that, calculate the anion gap. The anion gap equals sodium minus the sum of chloride and bicarbonate. Her sodium is 140. Her chloride is 104. Her bicarbonate is 16. So the calculation is 140 minus the quantity of 104 plus 16. 104 plus 16 equals 120. 140 minus 120 equals 20. Her anion gap is 20. That is elevated. So this patient has an anion gap metabolic acidosis. We now have evidence of two processes. She has respiratory alkalosis because her carbon dioxide is low, and she has an anion gap metabolic acidosis because her bicarbonate is low and her anion gap is elevated. But we still need to determine whether the low carbon dioxide could simply be appropriate compensation for the metabolic acidosis. That is where Winter's formula comes in. For metabolic acidosis, the expected carbon dioxide is approximately 1.5 times the bicarbonate plus 8, with an acceptable range of plus or minus 2. Her bicarbonate is 16. 1.5 times 16 is 24. Add 8. The expected carbon dioxide is approximately 32 millimeters of mercury. An acceptable range would be roughly 30 to 34. But her actual carbon dioxide is 24. That is much lower than expected. She is blowing off more carbon dioxide than compensation alone would explain. Therefore, the respiratory alkalosis is not merely compensatory. It is a second primary acid-base disorder. So the final classification is mixed respiratory alkalosis and anion gap metabolic acidosis. That is answer choice C. Now let's identify the pivot clue. The tinnitus is important because it points towards salicylate toxicity, but tinnitus is not the clue that proves the acid-base classification. The decisive clue is that the measured carbon dioxide is substantially lower than the expected carbon dioxide calculated using Winter's formula. The metabolic acidosis should produce a compensatory carbon dioxide near 32. Instead, the measured carbon dioxide is 24. That discrepancy proves that there is an additional primary respiratory alkalosis. The elevated anion gap is another critical clue because it shows that the low bicarbonate cannot simply be dismissed as compensation. Choice A is acute respiratory alkalosis with appropriate metabolic compensation. This is probably the strongest distractor. It is tempting because the patient is tachypnic, the carbon dioxide is low, and the pH is alkalemic. All three findings support respiratory alkalosis. The problem is that this answer does not explain the elevated anion gap. Her bicarbonate is 16 and her calculated anion gap is 20. That tells us there is a separate anion gap metabolic acidosis. So choice A identifies one real process but incorrectly treats it as the complete explanation. If you chose A, you probably recognized the dominant process but stopped too early. Choice B is anion gap metabolic acidosis with appropriate respiratory compensation. This choice also contains a major part of the truth. The patient absolutely has an anion gap metabolic acidosis. The problem is the claim that the respiratory response is appropriate compensation. Winter's formula predicts a carbon dioxide near 32. The actual carbon dioxide is 24. That is much lower than expected. So the patient has more respiratory alkalosis than compensation alone can explain. If you chose B, you may have correctly calculated the anion gap, but stopped before testing compensation. Choice C is mixed respiratory alkalosis and anion gap metabolic acidosis. This is correct. The elevated anion gap proves the presence of an anion gap metabolic acidosis. The carbon dioxide is lower than Winter's formula predicts, proving a separate primary respiratory alkalosis. Salicylate toxicity is classically associated with this combination. But the strongest reasoning does not depend only on memorizing that association. The laboratory values independently prove both processes. Choice D is mixed respiratory acidosis and non-anion gap metabolic acidosis. This conflicts with the data in two ways. Respiratory acidosis requires an elevated carbon dioxide. Her carbon dioxide is low. And the answer calls the metabolic process non-anion gap, but her anion gap is elevated. Choice E is metabolic alkalosis with appropriate respiratory compensation. This may attract students who focus almost entirely on the alkalemic pH, but a primary metabolic alkalosis requires an elevated bicarbonate. Her bicarbonate is low. The alkalemia is being driven by the low carbon dioxide, not by a high bicarbonate. Now let's go one level deeper. A traditional review might tell you that you missed an acid-base question, but that does not tell you what needs to be fixed. Different wrong answers point toward different reasoning breakdowns. If you chose A, you probably recognized the first correct process and stopped too early. If you chose B, you probably identified the metabolic acidosis, but did not finish the compensation analysis. If you chose D, the error may be more foundational. If you chose E, you may have overweighted the pH and ignored which variable was actually producing the alkalemia. Now think back to whether you changed your answer. Suppose you initially selected choice C, then changed to A or B. That is different from never recognizing the mixed disorder. You may have completed the reasoning correctly and then talked yourself out of the answer because a simpler diagnosis felt safer. That could reflect uncertainty with mixed disorders, poor confidence calibration, or a tendency to abandon correct reasoning when a familiar distractor appears. Now let's look at the decision fork. Imagine the same patient had a bicarbonate level of 16, but the carbon dioxide were 32 instead of 24. Winter's formula would tell us that a carbon dioxide of 32 is appropriate compensation for the metabolic acidosis. In that version of the question, answer choice B would be correct. But in the actual question, the carbon dioxide is 24. That is too low. That is exactly where answer choice B breaks. Here is the reusable rule from this question. In acid-base problems, never name the disorder from the pH alone. Identify the dominant process. Calculate the anion gap. Test compensation. Then decide whether the disorder is simple or mixed. A shorter version is direction, gap, compensation, commit. During your next acid-base question block, write down 4 lines before choosing an answer. First, is the patient acidemic or alkalemic? Second, is the dominant process respiratory or metabolic? Third, is the anion gap elevated? Fourth, is compensation appropriate? Only then commit to the final classification. And if you miss a question, do not simply write review salicylate toxicity. Ask what actually happened. Did you stop after identifying one process? Did you forget to calculate the anion gap? Did you calculate the gap but skip the compensation check? Did you anchor on the pH? Or did you initially reason correctly and then change your answer? Each of those errors requires a different correction. This question was not difficult because it lacked enough information. It was difficult because several correct observations had to be placed in the right sequence. The patient was alkalemic. She had a respiratory alkalosis. She also had an anion gap metabolic acidosis, and the compensation calculation proved that both were primary processes. That is why the correct answer is mixed respiratory alkalosis and anion gap metabolic acidosis. A missed question does not always mean you forgot the medicine. Sometimes you recognize the diagnosis but stopped too early. Sometimes you overweighted one value. Sometimes you skipped a calculation. And sometimes you changed away from the answer your own reasoning had already supported. MDSteps is designed to help identify that difference. You can try a free step-style reasoning diagnostic using the link in the description. After you answer, MDSteps will show you the pivot clue, why your selected answer was tempting, where that answer breaks, and the reasoning rule you can use on the next question. I'll see you in the next video.